Welcome to Chemistry with Caroline. In this video, we're going to look at the Friedel-Crafts Alkylation reaction. This reaction is an electrophilic aromatic substitution reaction. In this case, we're substituting out an H for an alkyl group. In the particular example that I've given, we have this tert-butyl group attached to the chlorine that will eventually become the leaving group, and so that's the alkyl group I transfer. There's a variety of alkyl groups that you can transfer, but this reaction proceeds through a carbocation intermediate, and so it is susceptible to rearrangements and has some limitations. So let's go to the next slide and we'll take a look at how the mechanism works. So because of the stability of aromatic compounds, they're not particularly reactive, and so generally for these EAS reactions, we're going to need to generate a really good electrophile. And so that can happen by putting in a Lewis acid catalyst, which can expedite the rate of the leaving group leaving. So this aluminum chloride is my electron acceptor, and so it's going to be my Lewis acid. And then this alkyl chloride is going to be my Lewis base. It's the electron donor. So the chlorine will donate electrons to the aluminum, which has an empty p orbital, and that will give us a structure that is a Lewis acid base complex and generate a really good leaving group, which will allow for our electrophile to be generated. So here's my Lewis acid base complex, and essentially what I've done here is just made a good leaving group that will generate my electrophile. So in any given time, there's not a lot of this complex. You can see it'd be less stable than the two reactants, which are neutral, but there is a small amount. And as it gets used up, the equilibrium shifts to make a little bit more. So once this is generated, now that whole group is going to pop off, and that is going to make the carbocation intermediate, in this case, this compound, that is going to act as the electrophile for our reaction. So now that a good electrophile has been generated, the benzene ring will attack. This is the slow step because aromaticity is disrupted. And that will generate this intermediate. This is the rhenium ion, and it can share that charge around the ring to help stabilize. So those electrons can go there. So this whole structure, these three structures, these make up the rhenium ion intermediate. And then the last step and the fast step would be deprotonation. And so I'm going to just redraw this molecule over here in sort of the last way that I drew it. So here's this positive charge. And so then what was the leaving group is going to come in, and the electrons between the aluminum and the chlorine can come out and grab that proton, and then these can fold over to restore aromaticity. And that would give my final product, this is the fast step because of that restoration of aromaticity. And there is my alkylated product, plus I have a byproduct of HCl, which is usually in gaseous form during this reaction, and my catalyst is regenerated in the process. So plus HCl plus aluminum chloride. So this reaction works really well if there is not a possibility of rearrangement with the initial carbocation that you generate. But if there is a possibility of rearrangement, you can end up getting a mixture of products that are similar, and so they're very difficult to separate from one another. So I've given here an example of a secondary carbon that has a leaving group on it, and then next door there's a tertiary carbon. And so if we think about the complex that would be formed here, I would generate this compound, which has that good leaving group in the Lewis acid base complex. So these electrons could go onto the chlorine, and that would initially generate this secondary carbocation, but I have a more substituted tertiary carbon right next door. So a hydride shift is possible and in fact probable. So if that hydride comes over here, that gives me the carbocation there. So I have two electrophiles now, and if I have two electrophiles, then I can get two possible products. The major would be the one that is more substituted. So let's number on this original compound. So 1, 2, 3, and then 4. And then I'm just going to keep the numbering the same. So you can see that the place where the carbocation is has changed from carbon 2 to carbon 3 as I've drawn it. So now you can imagine that the two possible products I would get would be this one, which is the original carbocation. So here's 1, 2, 3, and 4. And I could also get the product from the rearranged carbocation. And that, if I numbered it the same way, would be 1, 2, 3, and 4. And that would be the major product because of the more stable tertiary carbocation electrophile that was attacked. So that's a look at the Friedel-Crafts alkylation reaction. It's a great way to introduce an alkyl group, but it works best if there's no possibility for rearrangement with the carbocation electrophile that it proceeds through. If you found this video helpful, please like, subscribe, and share with your friends. Thanks.